It is a section 7.4, Gauss elimination with pivoting. The technique requires row interchange operations. Here we have a definition for permutation matrices. Permutation matrices are closely related to row interchange operations. A permutation matrix is a matrix that has exactly 1, 1 in each row and each column, all other entries being 0. In the matrix, only one entry is 1 in each column and each row. So such matrix can be obtained by scrambling rows of the identity matrix. Here we have this fact. If P is a permutation matrix, then P transpose P and P transpose are identity, which means that P is non-singular and P inverse is P transpose. So P is an orthogonal matrix. You can prove it quite easily. For instance, you can check this, and Pi, Pj, 2 columns. If you take the dot product, then you can easily see that the value is either 1 or 0. When they are the same, is 1, and different, then the value is 0. Quite easily you can check that. Here we have a claim. PQR square permutation matrices and A has the same size. Then PA, a permutation matrix P is multiplied from the left-hand side as A with its row permuted. So left multiplication makes the matrix row permuted. And if you multiply right side, then now the column must be permuted. Determinant of P, also Q, the same, must be either +1 or -1. If you make product of 2 permutation matrices, then also it is a permutation matrix. Also, this claim can be easily proved. Let's see this one. A is a square matrix, and A hat is a matrix obtained from scrambling the rows of A. Then you can show that there is a unique permutation matrix P such that A hat is P multiple from left-hand side to A. So row scrambling is exactly a kind of permutation matrix multiplied from left-hand side. Also, you can prove this one quite easily. Here, hint is given, and you can check it. Gauss elimination with partial pivoting applied to a matrix, square matrix, produces a unit lower triangular matrix L, an upper triangular matrix U, and a permutation matrix P, such that now for PA, it can be LU factorized, LU. We are using a head notation, but here the idea is during these operations, the algorithm, the row permutation is happening, and then eventually later on we end up with LU factorization then that can be considered as in this way. First, we multiply the corresponding permutation metric, and then for the permitted, row permitted metric, we try to get LU factorization. But in the beginning, we don't know what it is. So just apply LU factorization, and during the computation, we try to make the required row interchange, and then now we can end with LU factorization. But mathematically, we can say in this way, first permitted, and for the row permitted metric, we can make LU factorization without any further row changes. Of course, this equation can be written in this way, right? Because the inverse of P is P transpose. Once A is singular, then now U is a singular. And U is not non-singular, then A is non-singular. You can easily see that. You can use MathTalent or Python. When you try to use MathTalent, now the output is given in this way. Here, LUP, and the command is LU. In Python, in SciPy, package linear algebra, and you can find LU. And in this case, P first, PLU, the order, different order. So be careful when you are using one of these command. Now let's see an algorithm for solving AX equals B using Gauss elimination with partial pivoting. First, we factorize A into P transpose LU. P is the permutation metric, and L is unit lower triangular metric, and U is a non-singular upper triangular metric. Of course, when it is non-singular, we can solve the equation uniquely. After getting this factorization, and now we can solve it. AX can be written in this way, so it is B. So first we multiply P on the right side, and then L inversion, and finally U inversion to get the solution X. The P multiplication is the permitting right side B, the same as for A, so that if you imagine the augmented metric, then also right side B is permitted exactly same as for rows of A. And then now L inversion is for the elimination or for the substitution, and U inversion is the back substitution. Okay. In theory, once A is non-singular, then there exist permutations P1 and P2, and a unit lower triangle metric L and a non-singular upper triangle metric U, such that P1 A P2 is LU. But in this case, once it's non-singular, then U is non-singular, and in theory, only one of them is required, necessary. P1 multiplication in front of A means row interchange. Now P2 means it's column interchange. So along with one of them applied, either left side or right side, the metric can be LU factorized. That's the theory. P1A reorders the rows of A, and AP2 reorders the columns of A. And once you apply both sides, the permutation matrices, then it reorders both columns and rows. Okay. Now, here we have a remark for partial pivoting. Partial pivoting is when you are choosing, now right side is identity. Okay, let's say it is identity, so that only row interchange is applied. Then the manner is, for example, in the beginning, now A11 is largest entry. Okay, originally A is given here in this way. So here from the first column, in the beginning, this is a pivot. Now for this column, among these entries, we'll try to take the largest entry in modulus so that the row is moved to the top. And of course, there's go down. So interchange, row interchange is made such that A11 is the largest entry in absolute value. Of course, along the column, it is searched. And after that, here we try to eliminate the below entries. So that means that in LU factorization, here once we try to make LU factorization, then below this entry must be less than 1. It's not really larger than 1 in modulus, because in modulus this is already largest, so that the ratio must be not larger than 1 in modulus. Okay. And for each stage, okay, now keep going, go down in pivot, any kth level. Now we try to search below the column, and among these entries, largest one is chosen and row change is made. In this way, and by searching only column and try to make the largest entry on the pivot position, such algorithm, Gauss elimination, is called Gaussian elimination with partial pivoting. This algorithm guarantees that all entries of L are bounded by 1 in modulus, because we try to interchange the rows in that way, because for each column, now in pivot column, largest entry will become the pivot value in modulus, so that it is really guaranteed, right? Here the name is partial pivoting. That is now the counterpart of the complete pivoting. In choosing the pivot value, now rather than only searching the column, and try to search over whole matrix, and then largest one will be moved here. In order to do that, row change, column change simultaneously required, so that here P1, P2 must be applied. And so that once LU factorization is going on, then each K level also for remainder part, this portion of the matrix, try to get the largest value over the this remainder part, and then try to move it to the larger value over there. And in this way, we may get pivoting. Such a pivoting technique is called complete pivoting, and the algorithm is the Gaussian elimination with complete pivoting. It's not much popular. Here with partial pivoting, we can do things quite nicely, so that complete pivoting is not really necessary. in most cases. Okay. Here we have an example. Find the LU factorization of A. We have a 3 by 3 metric. Already we considered this metric in earlier example. Without pivoting, now once here we have 3. Now ratio is considered in 3, which is this one. And that is the inverse operation of that row replacement. Second row is replaced by subtracting 3 times of the first row. And so that the minus 3 is the entry in elementary matrix. Now its inversion is plus 3. The corresponding entry is plus 3. So eventually it becomes ratio. Okay, ratio. And then ratio minus 2. And of course, here row operation must be applied. And again, one more time, here this becomes pivot. Now ratio is 3 over 4. And after the replacement, we reach this final L factorization. This portion is L along with diagonal entries being 1. And this upper portion is the matrix U. Now, if we apply partial pivoting, then for this pivot, the largest entry, and by searching the column, and largest one will be, okay, the row having the largest value in modulus will be moved to top. Here we have interchange. This first row, second row interchange to get that one. Now it's the largest value. And here the start Gauss elimination. So ratio is 1/3 and ratio is minus 2 over 3 and corresponding row operations. Okay, so we finished this first column. Now pivot is moved to over there. Now below we search and we can find that is larger one in modulus, so that now we interchange. So correspondingly we interchange this one and that one all together. So we recheck here. Be careful, of course this one also must be interchanged. Okay, so we reach this one, and then along with this largest value on the column, we eliminate that, and that is the operation. And here, if you see the row interchange, then first we make an first row, second row interchange, and later second row, third row interchange. So that is interchange the information, and that is here. Okay, we can make the matrix in this way. Okay, in the beginning, identity matrix, which is 1 0 0 0 1 0 0 0 1, and from this one 2 row interchanged, which is now 0 1 0 1 0 0 0 0 1, right? And then now from here, second and third one interchanged, so that now from this one 0 1 0 and third row becomes the second, so 0 0 1, and second row go down 1 0 0. So we end with this matrix, which is P. As you can see here, P is this one, and this portion is L along with diagonal entries becoming 1, and this portion is U matrix. As you can see, the entries here all are bounded by 1 in modulus. Okay, we can implement L factorization with partial pivoting easily in this way. Now, for that one, here we are trying to get, and the maximum is producing the maximum value and the index. So we try to get the below of the matrix and kth column each in kth pivot, and then now that is eventually in a whole matrix, and R is determined in this way, so that we try to interchange, and also we try to update the permutation matrix, and now we apply row operation, and in this way it is organized for this matrix. And here we have now LUP, the order is LUP. Then here we have for that one, for the matrix, this L, and there is U, and now this is P. Once we multiply now P transpose LU, then we'll recover the original matrix. Okay, finally, we'll consider computation of A inverse. Now, the program to solve A x equals B can be used to calculate the inverse of a matrix. The inverse of a matrix is not really frequently used when you try to solve this algebraic system, but sometimes you need to get inverse of a matrix. So when you have to get inverse of a matrix, then we can use the technique for solving the algebraic system. Once x is A inverse, then we can write in this way: AX equals identity. Now, in detail, A, x1 first column of x, second column, and so on. So then nth column. Now right side, there's E1, E2, there's unit vector, 1, 0, 0, 0, and 0, 1, 0, 0, 0, and so on. Now, so that this system of multiplication can be separated individually in this way: A, ith one, ith vector, xi equals ei. So we have that one. So A xi equals ei, and we have to solve this equation n times. So you can make L factorization, and then now for every ei, you can find xi, and then collect them to get A inverse. So that's the idea of getting A inverse. For this technique, we can count number of operations required. So flop. So if we try to check naively the required flops, then for L factorization, there's 2, 3, n cubed. And to solve n equations required, each one requires 2n squared, so that eventually it's 2n cubed. So the total cost is 8 over 3 n cubed. That is now naive operations required to get A inverse. But we can modify this operation in this way. For example, now in the beginning, ei, okay, ei is here, start with a 0, all the down, all is down 0, and then, and here ith one, this 1, again 0. Now, if you try to solve L yi equal ei, then right side is 0. So first, okay, first row of this one is L 1, 1, y1 equal 0, which means y1 is 0. Then second one is also, okay, that is, the second row is L21 y1 plus L22 y2. Again, is 0 again. Then now y1 is 0, so that no matter what it is, here y2 must be 0. Right? And of course, here diagonal entry is non-zero, so that y2 must be 0, and so on. So that for this one, you don't have to worry about the rows earlier than I. So upper rows can be ignored. Along with this operation, you can save some computation so that A inverse can be computed, and along with that cost 2n cubed. It's here not much, however, it's cheaper anyway. So getting A inverse requires 2n cubed, we can say. Okay, that's the end of the section. Thank you.